Alright, this is the video review for my in-depth analysis, and I'm looking at the SLED project from Purdue University. Contact information was easily available, and I have it separated into two categories, one above the line and one below the line. Above the line is or contact information for Purdue University and their SLED project. So there's a mailing address, phone, fax, email, and then down here I also have links to projects information. They have a STEM educational hub, and it's full of links and good information, lessons, things that you could do related to STEM and SLED. And then contact information for James Lehman, who is the IP person for their presentation. I've got a link to his faculty page, and then we've got his email, phone number, and his personal website, which also has good information about STEM and SLED on it. The summarization of the project. So I viewed the video, and I believe it was Mr. Dietz who deserves credit for locating this video. I looked and looked, and I didn't find too many videos that piqued my interest, surprisingly. A lot of the topics were, I might say, a little bit outside of the reach of most elementary teachers for their students. However, I saw the SLED project on Mr. Dietz's reviews, and that one jumped out at me, and it really connected. So the project that I watched demonstrated the use of SLED, which is science learning through engineering and design. And SLED can be thought of as an approach to integrated STEM in which the student learners gain their science knowledge and practice inquiry while solving engineering and design challenges. So the question is, does SLED connect to STEM practices? And I would say unequivocally, yes, it is a very good match. SLED involves defining problems and asking questions. In the video, there were some kids who they were given a scenario where a dog was hurt, and they had to figure out a way to move the dog or transport the dog without causing it further injury. And the kids naturally had to define their problems after that and ask questions related to it. Students plan, carry out investigations, and they produce artifacts whenever they do SLED projects. So that's a definite yes. There is room available for mathematical and computational thinking in SLED projects. I didn't notice anything being demonstrated mathematically in the video clip that I saw. It was mostly defining a problem, coming up with a possible solution, creating the solution, evaluating it, and then going back to the drawing board or refining it if necessary. But it wouldn't be a big leap at all for someone to integrate math and computational thinking into a SLED project. When it's performed collaboratively, as was done in the video, there's bound to be argument from or about evidence among the participants. Naturally, anytime you get a group of kids working together on a project, there's a room for argument to happen naturally, but what we're referring to here is argument about or from evidence. So the kids will have a chance to talk about different ideas for solutions, maybe test out a little subsystem of whatever plan or solution they have in mind, and then they can use the evidence and argue whether or not it is a good solution. There is always obtaining and evaluating and communicating information involved in the process for a SLED project. And finally, if the teacher requires it, there will be analysis and interpretation of data. Naturally, the kids are going to interpret and analyze what happens when they attempt to use their product or their artifact, as they said in the video. But you could also add to it a component where you would collect, analyze, and interpret data from the use of your project. So you could take it one step further and integrate math a little more into it. this was a graphic I took, I believe, from their video on the SLED process. So it starts here by identifying the problem. They call it above that problem scoping and information gathering. You move on to share and develop a plan. This is called solution formation or formulation or idea generation. And then it's time to create and test. So, and this is a big part of the process. I mean, all of these steps are important, of course, but probably creating and testing is going to take a good deal of time. It's solution production and performance, or they call it project realization. I like that term. We move on to communicating the results. So communication and documentation of performance results. So communication could be accomplished many ways, and it could be writing. And I posted a video that I thought was pretty good about communicating information in written form that I had a little chance to preview. You could also have the kids present to the larger group or present to the teacher, present to each other to document their performance and results. And then you can't see me doing air quotes, but I'm doing air quotes now. This is the optimization part where they improve and retest. And they may find that after they retest it, that it is still not as good as they want it, and you might wind up going back to improve and retest or optimize it again. And that process can be ongoing and painstaking, but there's a lot of value in that effort and that approach. Does SLED meet the demands of scientific inquiry? I would say it absolutely does. The learners do engage in scientifically oriented questions. The example here could be, how can we use simple machines to move a dog into a vehicle? You could examine it closer and look at the different parts, talk about compound or complex machines, and ask questions about that. Is it better to use an inclined plane that is steep or an inclined plane that has a gradual slope? What would be better for the injured dog? Evidence in SLED activities can be immediately observed as a response to your question. So if you develop a question, which ramp is the best one for the dog, you can perform your task once you've made a model of it and check it out and find out. There is definitely communication throughout the process, and as such, there is plenty of opportunity to explain what happened based on the evidence. All explanations can be connected to science content knowledge and principles. And last but not least, learners are constantly in communication to justify their explanations. It's not enough to just say this is the best way. They absolutely have to communicate and justify any explanations they have. So why I chose this project. First and foremost, as an elementary teacher, working with elementary age students, this project was a natural fit to me. As soon as I watched it, I didn't even have to watch it. I just saw the still frame of the first clip that they had for their display, and I recognized. I was like, this is what I've been looking for the whole time. The approach called SLED really spoke to me, and it matched very closely what I would like to see done in elementary schools to enhance learning. And further than that, what I plan to do to enhance learning in my classroom is use SLED. Also, I said that I can already see its process as an approach to a summer STEM camp that I'm going to be teaching. Now that I have a stated structure for the process of inventing solutions to open-ended problems, I can picture exactly how it will move the activities along and guide the learners in my class. It's a perfect structure for the class. And I can also see how it will be utilized, or how I can utilize this in my math class next year by giving students challenges that will follow this process and bringing science into the math curriculum to make a deeper environment for learning, which I think is just ideal for what we're going for in elementary education these days. So that's my project. I couldn't be happier to have found this approach and this project, and I want to thank Mr. Dietz again for posting it. I hope you enjoy it as well and you can find ways to use it in your classroom.